Hi there, this is exercise 7H. We're going to do it in two parts, I think. So this is the first look at cumulative distribution functions. Now we actually saw these in exercise 7D, so if you're not sure, you might want to go back and have a look at exercise 7D. And in exercise 7D, we looked at what a cumulative distribution function is. You should remember, of course, that cumulative means you're adding up as we go along. And with these, we're kind of adding up the probabilities as we go along. And for that reason, the maximum probability on these things is 1. It goes from 0 to 1. Whereas these PDFs, which we find, often written with a little f of x, these aren't really proper probabilities. They're called probability density functions. Whereas these CDFs, these definitely are. These are the probabilities as we go through a distribution up to the maximum of 1, probability of 1. So let's just remind you of this. So there's a starter for you. Find a cumulative distribution function of the continuous random variable x, which has a probability density functions as such. So you should recall that to find the CDF, which we normally write capital F of x. Now that is the integral. Now normally it's written from minus infinity to x. Which is a bit weird, of f of x dx. Now, in most cases, you don't have to worry about infinities and stuff. So here, for instance, it says, this is my PDF, and it goes from 0 to 1. So really, I don't have to go down all the way to minus infinity. I can start at 0. But I do have to go up to x. My function is 6x minus 6x squared, so fair enough, dx. And what do? Well, I add a power and I divide by the power. So if I add a power, I get 6x squared over 2, so I reckon that's 3x squared, minus, and if I add a power, I get 6x cubed over 3, I reckon that's 2x cubed. Now the little thing we have to be careful of, it goes from, and it won't always do this, so this is where you have to be careful, it goes from 0 to x. Now this is a nice function. So when I put 0 in, I get 0 out, and when I put x in, it doesn't change. So my answer here is 3x squared minus 2x cubed. But it's not always, particularly if I've got e to the exponentials or logarithmic or functions which, trigonometric functions like sine or cos, which when they integrate them, and then substitute numbers in, sine of, cos of 0 is 1. So you've got to be careful. But that's what I think the answer is in this case. Notice how I write it though. F of x starts at 0, goes up to 1. So for all values less than 0, we know that from this, it's going to be 0. For all values more than 1, it's going to be 1. Now this is pure fluke that it's the same numbers, so don't assume that it's the same numbers all the time. It just happens in my rather dodgy question that I invented just now. That's what it is. But the bit that I got, 3x squared minus 2x cubed, notice that's the bit in between 0 and 1. In between 0 and 1. So that's a cumulative distribution function. Now, many exam questions start with, if you like, f of x, lowercase x, or even the CDF, the capital F of x. And somehow they want us to convert this, transform it into a new variable y. Sometimes they want the PDF of that y, or maybe just the CDF, the cumulative distribution function of y. Now this then, it's important to understand what we've got to do. There is a kind of order to this. If, for instance, I'm given this to start with, remember this is the PDF, I can integrate it, as I just showed you how to do, to get the CDF, capital F of x. With a bit of, algebraic logic, I can convert that CDF into a different CDF. And we usually call that G. And the reason why it's different is because you notice the variable has changed. And usually there's a transformation that allows me to say, well, x equals 2y, or might be written the other way around. But there's a way to connect this variable to this variable. But that, in so doing, changes the CDF. Notice once you get to your CDF, a bit like from PDF to CDF you integrate it, if you want to, and quite often you do, if you need to go back from the CDF to the PDF, you can differentiate. It all depends what they want out of you. The tricky bit is definitely the second step, this what I've called the algebraic step. and that's converting f of x into g of y. So I'll perhaps show you how to do those via examples. But notice this is the basic premise of that we say that g of y is equal to, well, what does g mean? It's the probability of all values up to that point. That's the definition of a cumulative distribution function. It's the probability of y up to some point. So just bear that in mind, we'll need that. So this is an old exam question which I've randomly picked. A continuous random variable x has a PDF given by that. Okay, fair enough. The random variable, and notice this is the transformation I was talking about. It basically says y is some function of x. In fact, it's 1 over root x. So bearing that in mind, it says find the CDF of y. So that's what I need to do first. Well, the very first thing, before I can do any of this, is I need to find the CDF of x. So f of x. So remember what I said before, you have to integrate from the lowest number up to x of the function we've got. Now it's probably better writing that as 3 over 2 x to the half dx. So I'm going to integrate it, add a power, that gives me x to the 3 over 2. And you'll notice dividing 3 over 2 by 3 over 2 just simplifies things very similarly. It just becomes x to the 3 over 2. Quite like that. Now I'll put my 0 to my x in. And when I do that, 0 to the anything is 0. So I don't need to worry about that. So this just becomes x to the 3 over 2. That's my CDF of f of x. Now, having got that, what that means is, see, I can say now f of x is equal to x to the 3 over 2, if you like. And what I need to do is just, for a moment, think to myself, what does that tell me in terms of the probabilities? So let's start this then. What we've got is this knowledge, what I said before was that g, interesting I've gone back to g, but you need to. G of y, which is of course what I said I need to find first, I defined to be the probability that y is less than or equal to y, and that's probably your starting point every time. Now, bear in mind I've got an alternative version of y. I've now got y is 1 over root x, so I can just change that. The probability that 1 over root x is less than or equal to y. Now, I want to get the y on the left. I want to know something about the probability again. So this is the probability. Well, before I do that, actually, it might be easier. I'm trying to just get my head around what is easier. Let's turn it upside down. And I suppose what I'm doing is I've got 1 over root, if you imagine 1 over root x is equal to y, then I could switch these round, and the root x and the y would switch places. But in doing that, and I suppose I can, but in doing that, if I switch them around, I think the sign changes. And that's important that you understand your inequalities. And it becomes 1 over there. So root x is greater than or equal to 1 over y. Notice now, I don't like the square root, as I kind of hinted at before. So I'm going to square both sides, and that gives me x is greater than or equal to 1 over y squared. But I still come back to this idea, I don't particularly like the fact it's greater than or equal to. My definitions for CDFs are always less than or equal to. So I've got to get away from this, and the way I do that is I say it's 1 minus the probability that x is less than or equal to 1 over y squared. And this is actually, the reason why I've done this is because this is actually the definition of f, which is basically a probability about x. So since I've now got a probability that x is less than or equal to something, that's the CDF of f. So I can write that as 1 over y squared is substituted into f. Now bear with this because we just need to go a bit further. What is f when I substitute 1 over y squared into it? Well, I suppose I can just do this up here. Imagine I said f of, well, I know f of x is this, so imagine instead I put 1 over y squared in. Now when I put x in, I do x to the 3 over 2. So when I put 1 over y squared in, I do 1 over y squared. To the 3 over 2, I just follow the rule. Now, if I square something but then square root it again, which of course that means I get 1 over y, but I've also got a cubed, so I've got a cube top and bottom. Cube in the top doesn't matter, 1 over y cubed though. So this is 1 minus 1 over y cubed. And I'll just write this now. I'm just going to write for y is greater than or equal to 1. Perhaps I might need to explain that in class. But certainly we need to care about the limits as well. So perhaps you can see that if this was less than or equal to, and we've switched it round along the way, certainly at the end we have, perhaps it makes sense for y now to be greater than 1 rather than less than 1. But we'll come back to that later. Now this, remember, is g of y. And this is actually the answer for g of y. But it's not the answer they've got. They've got a lowercase g of y. So just bear in mind, I've said then that g of y equals, what was it again? It was 1 minus 1 over y cubed. So if I want to find little g, the PDF, I have to differentiate this. And differentiating that, well, you basically add a power. Differentiate, you knock off a power, don't you? Here. So this perhaps would be better written as 1 minus y to the minus 3. Differentiate the 1, it disappears, so that's 0. This becomes minus 1 minus is a plus 3y to the minus 4. And that's probably better written as 3 over y to the 4, which I think is what they had originally. Yes, it was. Notice that's lowercase. So we've got two answers now. This is the CDF, and this is the PDF of y. Interestingly, we started off with the PDF of x, and we've managed to go all the way over there. Now, last part of this question says part 2. It says, now find the expectation of y squared. And to do this, you should recall that if you ever want to find e of x for some function f of x, notice this is written in lowercase, so it's a PDF. If we ever do this, we need to say, well, it's the integral, and you might remember inserting an x into there and writing x f of x dx for the limits. So I'd do the same here. The slight difference is, if I ever wanted to find e of x squared, you have to substitute x squared in there. So you can see whatever function you're looking at for the expectation, you have to squeeze that in x. That's why the x went in. So here, because it's in y's, I'm going to do the integral of y squared times by 3 over y to the, notice I'm using the PDF again, it's the lower case. So 3 over y to the 4 dy, I suppose. And the limits were, I think, 0 to 1. Might check that in a bit. Anyway, so this was actually, I think I made a mistake there. And I said that here, didn't I? I said this was true for y is greater than or equal to 1. It'd switch around, so I better take account of that. It's y and upwards, so 1 to infinity. Nearly went wrong. Anyway, so and again, I can talk more about limits next time. So when you do this, obviously it's the integral from 1 to infinity, assuming I explain those limits properly in lesson. But you can see they cancel with some of them, and I get 3 over y squared, which is the integral of 3y to the minus 2 from 1 to infinity dy. Now, if I integrate 3y to the minus 2, I add a power, which is actually 3y to the minus 1 divided by minus 1, which is minus 3 over y. Notice the numbers you've got to put in are 1 to infinity. Now 1 to infinity, if I put a massive number into this, 3 divided by a massive number is going to be 0. At minus 3 minus 3 divided by that 1, I reckon that gives me an answer of 3. Let's see if they get 3. Yes, they do. Actually, they've given two methods. Looking at that, you could have done it using x's. I didn't. I used this method. And this method is fairly standard. You've just got to get your head around it. Now, we have only looked there at one question, and it's taken me, well, I did a little starter exercise, but it's taken me 15 minutes to do it. So we'll do more of this in lesson, but that should be our introduction and perhaps speed things up during the lesson.